So when your spring is kept vertical like this, okay, and then if you add a block, it will stretch, right, by some distance. Let us call it x naught. Now in equilibrium, mg will be balanced by the tension force here, and the tension force here is k into x naught, right? So in equilibrium, your kx naught, which is tension, will balance mg, correct? So right now it is in equilibrium. Now if you further pull this down by x from equilibrium, if you further pull by x, so let's say this was your equilibrium, and from here you have further pulled by x, then what is the total extension? X naught was already there. Now you have created extra displacement or extension x. So the tension force now will be what? K x naught plus x, because tension is spring force here and spring force is k into extension. Here extension was x naught from its relaxed length. This is called relaxed length. So because of this block, the tension force kx naught will balance your mg. But when you further pull it down by x from equilibrium, in SHM, the displacement x is measured from equilibrium, right, from mean position. So this is the tension force. So you can see the tension force now is more than before. Mg is same only. So what will be net force? Tension minus mg, and that will be equal to ma from Newton's law. If you substitute this tension force here, what will you get? Kx naught plus kx minus mg equal to ma. But kx naught will cancel mg because of this equation, right? Because kx naught was initially balancing mg. That means kx is equals to ma. That means a is equals to k by mx. So this must be your omega square. So instead of doing so much calculation, what we will try to remember is, whenever a spring is kept vertically in equilibrium, we already know mg is balanced by some initial tension here, this one. So instead of doing all this calculation, what we will do, whenever springs are vertical or they are at an angle, what we will do, we will pull this block from equilibrium by x. Due to this extra displacement, there will be an extra force. That extra force we will write as kx. Okay, spring force. This is the spring force which is extra. So that extra force will result in acceleration ma. So you will get the same equation here. So if you do this way, then what happens? You don't need to worry about mg. That is what I'm trying to tell. So whenever springs are vertical or angle, forget about mg. Just displace the block by x, calculate the extra tension, and that extra tension on the block will create acceleration according to Newton's law. And once you relate acceleration of the block with displacement of the block, you will get omega. Correct? So let us solve this question which you have asked. So these are two blocks A and B. Their masses are same, m. So right now the system is in equilibrium. So the tension forces, spring forces, and the weight components here and weight here, tension force here will all balance each other, right? So we will not worry about mg and all. What we will do, we will give a extra displacement of the block this side. Now in SHM, if block has displacement this side, this spring will stretch here. So spring net force will be this side. So acceleration will be this side. This is acceleration of block A. Right? In SHM, acceleration should be opposite to displacement from its mean position. Similarly, this block, let's say, has displacement y down. So acceleration of this will be up AB. Now, Because of displacement of this block A, this is the extra displacement, or you can say extra extension of the spring. So there will be an extra spring force, let's say K into X. And here also some extra tension will be created, T. These are all extra forces, okay? So mg and all I don't need to worry, as I told in the previous video. And if tension here is T, everywhere here T, T, it will be T, T. Then here what will be tension? 2T, right? And that will be acting this way. So now if I write Newton's law for block A, acceleration is this side, downside. So Kx minus T. This is the net force, which is equals to m into acceleration of A, equation 1. And for block B, if I write, I hope you understood. mg I am not drawing because this is the extra force, extra tension. So when you do in taking care of extra tension, you don't need to worry about mg. Please see the previous video nicely. So what is the net force? 2t, that will be equals to m into acceleration of B. This is equation 2. Now we need to relate this acceleration with this x, right? So we need to find a relation between this acceleration and this acceleration. For that we will use constant relation, summation t dot a is equals to 0. For this I have shared one video, please watch properly. So here tension is this side, acceleration is this side, so dot product will be minus t into a. And here tension 2t is up, acceleration is also up, so it will be plus 2t into AB, that will be 0. So if I take it that side, I will get acceleration of B is equals to acceleration of A by 2. Put this in this equation. So your 2t will be equals to m into, what is acceleration of B? Acceleration of A divided by 2. So tension will be MAA by 4. Now put this tension in this equation. So you will get Kx minus m acceleration of A by 4 equals to m into acceleration of A. If I take this one that side, I will get Kx equals to 5m acceleration of A divided by 4. So acceleration of A will be what? 4k by 5m times x. And therefore this must be your omega square. So omega will be under root of this, right?